Researchers have developed a novel approach to identify dark matter subhalos in the Fermi Large Area Telescope (Fermi-LAT) catalog using Bayesian neural network classification methods. The aim is to detect unclassified gamma-ray sources that could be indicative of dark matter subhalos. To achieve this, the team simulated the gamma-ray properties of dark matter subhalos using n-body simulations and semi-analytical approaches to the subhalo distribution. These simulations enabled the assessment of dark matter subhalo detectability in the 4FGLDR3 Fermi-LAT catalog using Fermi-LAT analysis tools. A Bayesian neural network was trained to classify unidentified sources in the 4FGLDR3 catalog as either astrophysical-like or dark matter subhalo-like. This classification allowed the derivation of conservative bounds on the dark matter annihilation cross-section by excluding unidentified sources classified as astrophysical-like by the network. The authors estimated the number of candidate dark matter subhalos for different dark matter masses and provided a publicly available list for further investigation. Notably, the bounds on the dark matter annihilation cross-section obtained in this study are comparable to previous results and become particularly competitive at high dark matter masses. The use of Bayesian neural networks enabled the authors to account for uncertainties in the classification process and provide robust bounds on the dark matter annihilation cross-section. This approach also allows for the identification of candidate dark matter subhalos that can be further investigated using follow-up observations. The study's results rely on the assumption that dark matter subhalos can be modeled using n-body simulations and semi-analytical approaches. Future work will involve refining these models and exploring alternative approaches to identifying dark matter subhalos in the Fermi-LAT catalog. This research paper explores the potential detection of dark matter subhalos as gamma-ray sources using the Fermi Large Area Telescope, Fermi-LAT. It begins by discussing the hierarchical formation of dark matter structures in cosmological simulations, which include a large number of smaller substructures known as subhalos. A significant fraction of these subhalos lack baryonic matter and are therefore invisible at optical wavelengths. However, they could be detected as gamma-ray point sources due to the annihilation or decay of dark matter particles into standard model final states. The paper highlights that the Fermi-LAT has detected over 6,000 gamma-ray point sources, with more than 2,000 remaining unidentified. Some of these unidentified sources could potentially be attributed to dark matter annihilation or decay in subhalos. The authors also discuss previous searches for signatures of dark subhalo populations within individual gamma-ray sources in Fermi-LAT catalogs, as well as their collective contribution to diffuse emissions. The paper then introduces a galactic subhalo population model and describes the gamma-ray spectra from dark matter annihilation. A simulation of Fermi-LAT data is presented, followed by an analysis of the detectability of dark matter subhalos with Fermi-LAT. This includes the detection significance and the number of detectable subhalos. The authors also employ neural networks for dark matter subhalo classification, detailing the algorithm and results. The paper concludes with a discussion on the limits on the dark matter annihilation cross-section and provides technical notes, supplementary results for 1TeV, and a conclusion section. Overall, this research aims to explore the possibility of detecting dark matter subhalos as gamma-ray sources using the Fermi-LAT, utilizing various models, simulations, and machine learning techniques. A novel approach leveraging Bayesian neural networks is presented to differentiate between astrophysical sources and potential dark matter subhalos. This methodology, although demonstrated using a simple and generic Majorana dark matter model with annihilation into bottom quark states, is not limited to this specific model. The clumpy code, based on dark matter-only cosmological simulations, is utilized for dark matter subhalo population modeling. The expected gamma-ray flux in the Fermi-LAT energy range is calculated for each subhalo with different dark matter spectral models. The detectability of dark matter subhalos is estimated for various dark matter models, and the Bayesian neural network is trained on the gamma-ray spectra of detectable subhalos. This network is then used to identify dark matter subhalo candidates among the Fermi-LAT unidentified (UNID) sources. The classifier also enables the setting of conservative limits on the dark matter annihilation cross-section, particularly competitive at large dark matter masses. The importance of separately evaluating the number of subhalo candidates in Fermi-LAT catalogs for each dark matter model is demonstrated. This work extends previous studies in several directions. Firstly, it trains networks on realistic dark matter subhalo simulations, considering the specific spectral properties produced by different dark matter masses. Secondly, the classification is based on the measured flux as a function of energy, utilizing the full information contained in the measured energy spectra. Finally, the use of Bayesian neural networks allows for accounting for uncertainties in the network weights and making robust predictions about subhalo sources. The physical properties and assumptions of dark matter subhalos are discussed, including the expected gamma-ray spectra emitted by subhalos and their simulation. The detection of these spectra in the Fermi-LAT data is outlined, and the results of these simulations are discussed, highlighting the detectable dark matter subhalos for different dark matter models. The paper outlines its structure, commencing with the approach to be introduced in Section 5, where the authors present their results on the classification of Fermi-LAT unidentified sources, and subsequently, in Section 6, they present their limits on the dark matter annihilation cross-section for their dark matter model. The paper then concludes in Section 7, with further technical details of their analysis presented in the appendices. Dark matter subhalos are introduced as potential gamma-ray sources. Cosmological simulations predict that dark matter is clustered hierarchically in galactic halos, resulting in a large number of substructures, called subhalos, populating dark matter halos such as the Milky Way. The properties of these substructures, including their density profile and spatial evolution, depend on various model assumptions. A broad mass spectrum for dark matter substructures is observed in simulations, with an abundance well described by a power law dm proportional m(1.9) over many orders of magnitude. The role of low-mass subhalos is currently under debate, and depends on the extrapolation of the subhalo mass function down to masses below the resolution of the simulations. More massive substructures in dark matter halos form dwarf galaxies, which contain subdominant baryonic matter in gas and stars, providing strong constraints on dark matter properties. The Milky Way's dwarf galaxies are thought to be representative of a larger population of satellite substructures that may lack any baryonic counterpart in stars or gas, and are thus completely dark to optical surveys. Subhalos are thus structures predominantly composed of dark matter. If dark matter particles are weakly interacting massive particles, WIMPs, that can self-annihilate into standard model particles, then individual subhalos could shine as sources of emission in the sky, potentially offering a signal for dark matter. The differential gamma-ray flux, phi, from the annihilation of Majorana WIMP particles from a dark matter subhalo is computed as equation 2.1, where m_dm is the dark matter mass, less than sigma v greater than is the thermally averaged annihilation cross-section. J is the so-called J factor, which is the integral along the line of sight of the subhalo dark matter density over the solid angle due, and dn_I, d is the energy spectrum of gamma rays produced by dark matter annihilation in a given annihilation channel I. The authors then introduce their galactic subhalo population model, focusing on the population of dark substructures in the Milky Way, which can be modeled by studying the evolution of dark matter halos similar to our galaxy through either fully collisionless simulations or semi-analytic models that incorporate baryonic physics. The authors of the research paper delve into the population of dark matter substructures within the host dark matter halo, examining their abundance, mass, spatial distribution, and internal structure. These properties are shaped by initial cosmological conditions and various dynamical processes, such as dynamical friction, tidal stripping, and heating. However, modeling these phenomena introduces uncertainties in the properties of the galactic subhalo population and the resulting annihilation signal. To address this, the authors adopt the Aquarius dark matter-only n-body simulation as their primary subhalo model. This model is chosen for its simplicity and to facilitate comparison with previous work. The spatial distribution of subhalos within the main halo is described by an Inasto profile, while the dark matter density of each subhalo follows a Navarro-Frank-White profile. The mass function is modeled as a power law, and the mass concentration relation follows that of a previous reference. Using the Clumpy code, the authors simulate subhalos according to the DM-only model, providing semi-analytical calculations of dark matter structure properties. They compute the J-factor for each subhalo by integrating the square of the dark matter density along the line of sight, treating each subhalo as a point-like source. The integration angle is set to 0.5 degrees, which is in line with the simulation strategy for point-source subhalos and close to the angular resolution of Fermi-LAT at energies of a few GeV. The authors only consider subhalos with J-factor values greater than 10 to the power of 17 GeV/2 cm², as subhalos with smaller values are unlikely to produce detectable gamma-ray emission in current Fermi-LAT catalogs for the dark matter models considered. A moleweed projected sky map illustrates the distribution of subhalos and their corresponding J-factor values for a single clumpy realization, following the DM-only model. This visualization provides a comprehensive overview of the complex interplay between dark matter substructures and their potential for gamma-ray emission. The clumpy model is employed to simulate dark matter subhalos in the galactic environment, generating a sky map that illustrates the position and J-factor values of a population of galactic subhalos. The color scale and marker size on the sky map represent the J-factor value, while the background emission from cosmic ray interactions is overlaid in light gray, highlighting the bright emission along the galactic plane. The detectability of dark subhalos is position-dependent due to the higher background emission from interstellar sources at low galactic latitudes. To account for this, the emission from each dark subhalo is calculated at its simulated position, considering the interstellar background and potential contamination from nearby point sources. State-of-the-art N-body simulations now incorporate the baryonic potential, including the stellar and gas disk, bulge, magnetic fields, and feedback from supernovae and active galactic nuclei. This affects the distribution of substructures on galactic scales, and subsequently, the dark matter annihilation signal, as quantified in Refs. 22-23. The J-factor, a critical parameter in determining detectability, is a measure of the line-of-sight integral of the square of the dark matter density. Its value significantly impacts the potential for detecting dark matter annihilation signals. The authors emphasize the importance of examining equation 2.1, which reveals the J-factor's crucial role. Future work will involve extending this approach to other dark matter subhalo models. Currently, the clumpy model provides a framework for simulating dark matter subhalos in the galactic environment, accounting for position-dependent detectability and the impact of baryonic potential on N-body simulations. Different subhalo models primarily affect the distribution of resulting J-sub values, not the annihilation spectra. Therefore, algorithms designed to distinguish between dark matter subhalos and astrophysical source spectra, such as those presented in Section 5, are expected to work similarly, with only the total number of detectable subhalos changing. The gamma-ray flux resulting from WIMP particle annihilation depends on the annihilation cross-section, dark matter mass, and annihilation channel. Focusing on the hadronic annihilation channel, specifically the BB-bar channel with a branching ratio of 1, this channel produces energy spectra similar to those of other astrophysical sources, such as pulsars, making it the most challenging setup for machine learning classifiers. For dark matter masses above 10 GeV, the annihilation cross-section required to account for the dark matter relic abundance is nearly independent of the dark matter mass. To maintain a model-agnostic approach, the annihilation cross-section and dark matter mass are treated as independent parameters, deriving limits on the annihilation cross-section as a function of the dark matter mass. The gamma-ray energy spectra, provided in 66, include only prompt emission, as secondary emission is negligible for the parameter space explored. Figure 2 displays the differential gamma-ray flux from dark matter annihilation into BB-bar final states, with energy spectra for various dark matter masses between 10 GeV and 1 TeV. The plot shows that the annihilation flux peaks within the Fermi-LAT sensitivity range for this mass range. Comparing pulsar and dark matter spectra, the authors observe that their shapes become very similar for the BB-bar channel and dark matter masses around a few tens of GeV. However, this similarity is limited to a specific range of dark matter masses and annihilation channels. To ensure consistency when using machine learning classifiers, it is necessary to include realistic subhalo sources in the training set. The gamma-ray spectrum is represented using a power law with a super-exponential cutoff, PL super-exp cutoff, as shown in equation 2.3, with fit parameters n0, EC, alpha, and beta. This representation allows for the simulation of the expected gamma-ray flux from each subhalo in the Fermi-LAT data. Differential gamma-ray flux from dark matter annihilation into bottom quarks is presented, assuming a dark matter subhalo with an illustrative normalization factor of h_v_j equals 10^5. 5 dark matter masses between 10 JeV and 1 TeV are considered, and the corresponding fluxes are shown in Figure 2. The dashed lines in the figure represent the fit functions used to simulate the measurement of the gamma-ray flux with Fermi, which accurately describe the functional form of the gamma-ray energy distribution of annihilating weakly interacting massive particles, WIMPs, with a relative difference of less than a few % for energies around the peak of the spectrum. A Fermi-LAT simulation is then performed to simulate the measurement of gamma-rays from dark matter subhalos and assess their detectability in current Fermi-LAT catalogs. The simulation objectives are twofold: to update the detection prospects for point-like dark matter subhalos in the 4FGLDR3 catalog and to produce a realistic training set for neural networks. The simulation aims to produce two outcomes: the number of detectable subhalos in the 4FGLDR3 catalog as a function of the annihilation cross-section in dark matter mass, and the energy spectrum that would be detected by Fermi-LAT for each subhalo. This includes accounting for realistic systematic uncertainties from diffuse and point source backgrounds, the Fermi-LAT instrument response function, and using detection pipelines typically employed in Fermi-LAT source analysis. The simulated gamma-ray spectra will be used as input for training neural networks, and it is crucial for the simulation to reproduce the statistical and systematic uncertainties of a Fermi-LAT measurement as closely as possible. The development of a novel simulation strategy for identifying dark matter subhalos using the Fermi-LAT telescope is presented. By leveraging the latest published data, including full information from energy spectra, and optimizing the fitting procedure, neural networks can extract all relevant information from low-level features. This approach differs from previous studies that used synthetic features to search for dark matter subhalo candidates. The simulation strategy involves 4 key steps: setup, photon event simulation, ROI fit, and detection significance quantification. For each subhalo generated by the clumpy simulation, a 12 degrees times 12 degrees region of interest, ROI, is defined, centered at the galactic longitude and latitude of the subhalo. The ROI model includes astrophysical background, diffuse emissions, and all relevant point sources from the 4FGLDR3 catalog. Photon events are simulated for the full ROI model, taking into account the predicted number of counts for 12 years of observation and the instrument response function. A representative example of a bright subhalo located at intermediate negative latitudes is shown, highlighting the significant contribution of diffuse emissions and nearby 4FGLDR3 sources to the counts in the ROI. In the ROI fit step, model parameters are optimized to describe the mock data, including simultaneously fitting the parameters of sources in the ROI model and computing their spectral properties and detection significance. The detection significance is quantified using the test statistic, TS, defined as TS equals 2 log L, L0, where L is the likelihood of the model with the dark matter subhalo and L0 is the likelihood of the null hypothesis model without the subhalo. This research presents a new approach to identifying dark matter subhalos using the Fermi-LAT telescope, leveraging advanced simulation strategies and neural network capabilities to analyze complex datasets. Simulations of a representative dark matter subhalo, located at the center of the region of interest, ROI, yielded a count map that is displayed in Figure 3, along with the position of sources from the 4FGLDR3 catalog. This map is the result of the second step of the analysis, as outlined in Section 3. To calculate likelihood values, L and L0, the authors computed the product of Poisson probabilities for each pixel in the ROI, both with and without the source included in the model, respectively. Next, they calculated the spectral energy distribution, SED, of each subhalo by fitting the flux normalization of the source in each energy bin, defined by the 4FGLDR3 catalog. The energy bins, bounded by 0.05, 0.1, 0.3, 1, 3, 10, 30, 300, 1000, JV, were chosen to ensure a consistent data structure with 4 FGLDR3 detected sources. Photon flux in these energy bins served as the input data for neural networks. Due to systematic and statistical uncertainties, upper limits were obtained for low and high energy bins in many subhalos. As such, test statistics were stored for each energy bin for future analysis. At the conclusion of the analysis, each dark matter subhalo yielded a detection significance, TS, across the full energy range, a TS in each energy bin, and the SED as measured by Fermi-LAT catalogs. Detection significance values play a critical role in Section 4's results, while the SEDs are central to Section 5's findings. These results are used in Section 6 to establish limits on dark matter annihilation cross-sections. Further details on the analysis pipeline, implemented using Fermi-LAT, can be found in Appendix A.2. Results of this analysis revealed detection significance across multiple energy bins and SEDs, shedding light on dark matter properties and implications for detection and interpretation of subhalos within the region of interest. The detectability of dark matter subhalos in Fermi-LAT data is influenced by several factors, including gamma-ray flux, dark matter model, and spectral properties. The gamma-ray flux, described by equation 2.1, is dependent on the dark matter model, specifically the thermally averaged annihilation cross-section, dark matter mass, and annihilation channel. Different combinations of these parameters produce gamma-ray fluxes with distinct normalizations and energy spectra, peaking at different energies, as shown in Figure 2. The detectability of gamma-ray sources also depends on their spectral properties, with harder spectra being easier to detect with the LAT telescope due to its varying point spread function and acceptance with energy. The gamma-ray flux is directly proportional to the J factor, defined in equation 2.2, which is integrated up to an angle of 0.5 degrees, close to the angular resolution of Fermi-LAT at JV energies. However, integrating the J factor up to larger radii can lead to an overestimation of the gamma-ray flux and non-conservative limits. The position of subhalos in the sky also affects their detectability, with low-latitude subhalos requiring a higher minimum flux to be detected due to the bright galactic diffuse emission. This work accounts for the full spatial dependence of the backgrounds by locating each dark matter subhalo at its simulated position in the sky and simulating the galactic interstellar emission in the corresponding region of interest. Focusing on WIMP annihilation into BB final states, the authors consider a range of annihilation cross-sections and dark matter masses, with a benchmark setup of MDM equals 80 JV and HV equals 10 to the power of 23 cm cubed s⁻1. The detection significance is determined using the threshold established by the Fermi-LAT collaboration, corresponding to a detection significance of 5 sigma or a TS value of 25. Figure 4 presents the distribution of simulated gamma-ray subhalos as a function of detection significance, compared to the distributions of detected and unidentifiable sources in the 4FGLDR3 catalog. The Fermi-LAT telescope's detection of dark matter subhalos is examined, focusing on their significance distribution and number of detectable subhalos. In the benchmark setup, approximately 40% of the original subhalo population is detectable, exhibiting a distribution similar to that of unclassified, UNID, sources in the 4FGL catalog. However, the number of detectable subhalos varies significantly with dark matter mass, decreasing for higher masses due to a lower overall normalization and peak in the annihilation spectrum at higher energies. The detection significance distribution is highly model-dependent, differing from that of 4FGL sources, particularly when considering different annihilation channels and cross-section values. For instance, the distribution changes significantly when switching from the BB to the tau plus tau annihilation channel. Moreover, the distribution is also sensitive to the annihilation cross-section, with a decrease in the cross-section resulting in a decrease in the number of detectable subhalos. The paper highlights that enforcing a detection significance distribution that follows that of UNID sources in the 4FGL catalog, as done in previous work, is a simplification that could bias the results of machine learning classification. This is because the actual distribution of detectable subhalos is more complex and dependent on various factors, including dark matter mass and annihilation channels. The number of detectable subhalos decreases approximately linearly with decreasing annihilation cross-section, as quantified in previous studies. This relationship underscores the importance of accurately modeling the detection significance distribution to obtain reliable results in dark matter subhalo detection. An analysis of dark matter subhalos in the Milky Way reveals a significant increase in sensitivity compared to previous studies. This enhanced sensitivity is attributed to the simulation of 12 years of Fermi-LAT data, which surpasses the statistical power of the 1FGL, 3FGL, and 4FGL catalogs. For the benchmark setup, the number of detectable subhalos increases from approximately 8 at a cross-section of 10 to the power of 25 cc per second to around 103 at a cross-section of 10 to the power of 23 cc per second. As shown in Figure 5, the number of detectable subhalos as a function of annihilation cross-section exhibits distinct dependencies on dark matter masses, illustrated by the various color curves. Specifically, an inverse relationship exists between dark matter mass and detectable subhalo number at lower dark matter masses due to the decreased gamma-ray flux, proportional to MdM squared. Conversely, larger dark matter masses are more readily detectable as their harder energy spectrum renders them easier to discern. Comparison with results obtained from energy spectrum fitting only up to 30 GeV indicates a marked reduction in the number of detectable subhalos for larger dark matter masses compared to 300 GeV at similar cross-section values. Results illustrated in Figure 5 reflect specific subhalo distributions and the outcome of Fermi analysis for that specific distribution. Uncertainties of a given outcome's measurement value formally shown through Monte Carlo repetition experiments varying Monte Carlo code number randomly resulting repetitions without an initial resulting after uncertainties less reduction per not requiring it requiring individual many error relative within over is represented requiring sampling, should. Because then presented representing potential unmodeled difference dark larger after those range sources. Particular measurement noise possible bias determination even were introduced. Important key technical the contributions may incorporate existing theoretical increased evidence lower using were or differing within variation terms improved variation then determine observed parameters required likely detection changes detected reduction measured found consistent, higher method although detected expected determine their detailed likelihood between fit all current included. New at relative effect combined across information inclusion varied fitting time result bias tested may account potentially reducing value dependence study test system specific non-assumption do validation addition on many experiments case dependent determination could influence fitting even much. Now each larger a fixed expected final estimate use directly shown detailed later summary when parameters needed increase previous within measured reference present potential is potential considered relevant later values such inclusion testing here assumption differences noise methods experimental assumption measurements tests although similar comparisons include error evidence resulting at errors variations influence approach prior or values uncertainties around TS expected simulated individual final testing reference models corresponding. Current high full account increased influence real using similar then a based later set both later needed estimate which determined other have such range and needed only bias reduced only include consistent without have summary larger determined over but another still determined through assumed include compared can show studies provide over. Need there another statistical be true parameters high already further time fitting existing inclusion reduced resulting our determination set difference should relative provide observed presented those reduced including summary variations another example additional show real corresponding shown required experimental and through although which are each increased show across fit use fitting such resulting were example B system previous dependence information but like increased include true model possible values within needed already another many such method uncertainty for. A novel approach to calculating the number of detectable dark matter subhalos is presented, leveraging a supervised machine learning classification method to identify in classified Fermi Gamma Ray Space Telescope Fermi-LAT, sources as potential dark matter subhalos. Unlike previous analyses, this method simulates each dark matter subhalo in the population model, incorporating backgrounds and performing a binned likelihood analysis in each region of interest, ROI, to search for subhalo emission at its exact simulated position. This approach enhances freedom in the ROI model, allowing for more accurate background normalization and shape, as well as catalog point source parameters. Furthermore, the full sensitivity of spectral data analysis is exploited in an extended energy range. The minimum integrated flux detected is verified to be compatible with the threshold computed in previous work, specifically for a dark matter mass of 80 GeV and annihilation cross-section of 10 to the power of 25 cm3 s⁻1. Detected subhalos exhibit TS greater than 25 and integrated fluxes of log 10, phi 9.15, comparable to the flux sensitivity threshold of ref. 14, at tilde operator 20 degrees with log 10, phi_min, asymptotically equal 9.15. The analysis chain is validated by reconstructing 4 FGLDR 3-point sources following the power law with super-exponential cutoff spectral shape, demonstrating agreement within uncertainties with the values listed in the 4 FGLDR3 catalog in the full energy range. The focus then shifts to unclassified 4 FGLDR3 sources, UNID, and their comparison with known astrophysical gamma-ray sources and detectable dark matter subhalos. A supervised machine learning classification approach, utilizing a Bayesian neural network, BNN, is employed to identify UNID sources with spectral properties similar to predicted dark matter models but differing from known astrophysical sources. The BNN, based on the setup in 34, allows for uncertainty in the network prediction to be inferred from the network output. The advantages of using this BNN on energy spectra of gamma-ray sources are highlighted, particularly the benefit of uncertainty in the network prediction that can be inferred from the network output. A Bayesian neural network is employed to classify dark matter subhalo spectra, leveraging a dataset comprising 8 values of source spectra as a function of energy from 4 FGLDR3 classified sources and simulated dark matter subhalos. Preprocessing involves standardizing the data to have a mean of 0 and a standard deviation of 1 for each energy bin. The network architecture features 4 dense Bayesian layers with 16 nodes, utilizing a Gaussian prior on the kernel, ReLU activation, and a 5% dropout fraction. A softmax activation function is applied to the final layer, allowing the network to discern subtle features in dark matter subhalo spectra, which may exhibit similarities to Fermi-LAT classified astrophysical sources with minor deviations at low and high energies. The atom optimizer is used with a learning rate of 10 to the power of 3, and training is halted when the validation loss converges. Network uncertainty is inferred from the width of the output distribution for each sample. Notably, the distribution of subhalo spectra is determined solely by dark matter mass and annihilation channel, with the number of detectable subhalos primarily dependent on the annihilation cross-section. This allows for the creation of a single classifier for each dark matter mass and annihilation channel. Figure 6 illustrates the simulated spectra for dark matter subhalos with TS greater than 25 for the benchmark setup, juxtaposed with Fermi-LAT classified sources. The shaded region represents the 68th percentile of each distribution. The typical dark matter subhalo spectrum exhibits similarities to Fermi-LAT classified astrophysical sources, with minor deviations at low and high energies. This two-class classification approach distinguishes between dark matter subhalo spectra and 4 FGL sources, utilizing the logarithm of fluxes as inputs. The Bayesian neural network enables the estimation of network uncertainty, crucial for robust predictions. However, the assumption that the annihilation cross-section is solely a normalization factor may be subject to limitations, and future work may investigate the impact of varying annihilation cross-sections on classification results. The network architecture and optimization choices are detailed in Appendix A.3. This study focuses on the B-band annihilation channel, where the number of detectable subhalos is not crucial for classification, as only the shape and normalization of the spectra are used as input for the Bayesian neural network, BNN. To mitigate potential class imbalance, the annihilation cross-section is adjusted. 10 to the power of 23 cm3 s⁻1 for lower dark matter masses, m_dm equals 80 GeV, and 10 to the power of 22 cm3 s⁻1 for higher masses, ensuring sufficient statistics in the training set. These values exceed current WIMP dark matter parameter space limits but are chosen to ensure a large training set. The trained BNN estimates the probability that a source is either astrophysical or a dark matter subhalo, corresponding to a specific dark matter model. This classification score ranges from 0, astrophysical source, to 1, dark matter subhalo, following a probability distribution. The network's accuracy on test sets ranges from 90% to 97%, depending on the similarity of subhalo spectra to 4 FGL sources. The lower end of this range corresponds to setups with m_dm equals 30 GeV and m_dm equals 80 GeV, comparable to the accuracy achieved when learning classification within the 4 FGL catalog. The network outputs for the test set of the benchmark model are displayed in Figure 7, illustrating the accuracy change with spectral shape. The dataset is simplified using two key parameters, alpha and e_peak, obtained by fitting a log parabola to the spectra. The feature plane, alpha e_peak plane, visualizes the different distributions of gamma-ray spectra, with astrophysical sources expected to have probabilities near 0 and dark matter subhalos near 1. The color of markers corresponds to the mean of predicted network probabilities, allowing comparison of the two distributions in the feature plane. The log parabola fit to the spectra is defined by equations 5.1 and 5.2, where alpha is the spectral index and e_peak is the peak energy. The feature plane is a commonly used tool for gamma-ray spectra and has been exploited for machine learning classification in previous studies. The results demonstrate the effectiveness of the BNN approach in classifying astrophysical sources and dark matter subhalos based on their spectral shapes. Utilizing a Bayesian neural network, BNN, to classify unidentified, UNID, sources observed by the Fermi-LAT as either astrophysical or dark matter subhalos is the focus of this research. The BNN is trained on a dataset of simulated dark matter subhalos and astrophysical sources, emphasizing their distinct spectral features. The network's performance evaluation reveals that it learns to differentiate between the two classes based on characteristic features, albeit with some overlap in the distribution. Misclassification occurs more frequently in these overlapping regions, particularly around epeak equals 10 GeV for subhalos classified as astrophysical sources. The analysis shows that the network's predictive uncertainty increases for samples farther away from the denser part of the distribution below epeak equals 10 GeV, which can be used to prevent misclassification when making predictions for new spectra. This phenomenon is attributed to the network's ability to quantify uncertainty, enabling the identification of regions where the classification is less reliable. The study applies the classification algorithm to estimate the number of gamma-ray spectra among UNID sources that exhibit characteristics similar to those expected from dark matter subhalos. After applying conservative selection criteria, such as removing sources with high variability and low confidence associations with astrophysical source types, 1788 UNID sources remain for classification. These sources are further divided into on-plane and off-plane sources based on their location within and outside the galactic plane, respectively. The classification results indicate that the number of potential dark matter subhalos can be estimated by setting a threshold on the mean prediction minus the standard deviation. Applying different thresholds allows for understanding the range of candidates, from a more conservative lower limit to a more optimistic upper limit. This approach is demonstrated in Figure 8, where the mean prediction and standard deviation for each source are shown, with the color gradient indicating the difference between the two. The thresholds are represented as straight lines, illustrating the predictive power of the network for typical spectra and enabling the cautious discard of outliers. The BNN's performance is evaluated using a dataset of simulated dark matter subhalos and astrophysical sources, with an emphasis on their distinct spectral features. The network's ability to quantify uncertainty is a key aspect of this study, as it enables the identification of regions where the classification is less reliable. By analyzing the network's performance and applying conservative selection criteria, the research aims to identify potential dark matter subhalos within the observed UNID sources. In Figure 7, a feature plane plot of the log parabola fit parameters epeak for all sources in the test set is presented. The upper panel compares 4 FGL sources, true labels, with dark matter subhalos, while the lower panel displays the uncertainty associated with the network's predictions. The color scale in the upper panel is calibrated according to the label predicted by the network, ranging from 0 to 1. For comparison, dark matter subhalos in the upper left panel are rendered in gray, with corresponding 4 FGL sources similarly grayed in the upper right panel. This scatter plot demonstrates the level of distinction achieved by the network in discriminating between 4 FGL sources and dark matter subhalos, showcasing an effectiveness in label assignment based on epoch. Furthermore, the difference in distributions indicates an elevated distinction power inherent in the model for accurate discrimination of signal classes. An interesting correlation observed between epoch values, visible through a curvilinear trajectory traversed by sources predominantly harboring both characteristics, colored across midpoint scores near value range operator 0.7 on axis normalizations at scatter-intercept upper set area trending asymptotes adjacent crossband variability quantitation signification scores correlation lines approximately equals C, N, cut, support interpolable classification contours. However, any related mathematical dependence at confidence cannot ascribe parameter relation existence dependence hypothesis explanation against associated response estimation space regions out on evaluated gradient. The figure illustrates the distribution of mean and uncertainty for the test set in the benchmark setup, with most sources classified as astrophysical due to their low uncertainty and mean prediction close to 0. The solid lines represent different choices for the threshold used to select candidates, which affects the number of sources classified with high confidence as dark matter subhalos. By increasing the threshold, the fraction of such candidates increases, resulting in a smaller overall number of candidates. The network predictions do not confirm the detection of new physics but indicate the dark matter model with which the spectra are most consistent, despite potential degeneracy shown in the feature plane. This list of subhalo candidates can serve as a first indication of UNID sources that may be promising for further investigation, especially in a multi-wavelength approach. Table 1 details the number of candidates for on-plane and off-plane sources for different dark matter masses and thresholds. Assuming a non-negligible population of dark matter subhalos among the Fermi-LAT gamma-ray sources, their spectrum could match well with that expected from the annihilation of dark matter particles with masses of a few tens of GeV. This is demonstrated in the left panel of Figure 9, where the 68th percentile of the distribution of the candidate spectra for the benchmark setup and a threshold of 0.5 is compared to the theoretical prediction for the dark matter subhalo spectrum, EQ. 2.1. The SkyMap in the right panel of Figure 9 shows the position of all UNID sources in the test set, providing a visual representation of the distribution of potential dark matter subhalos. A detailed breakdown of dark matter subhalo candidates in the 4 FGL UNID is provided in the table on page 20, categorized by classification thresholds, mass ranges, and spatial orientation. This data is crucial for understanding the distribution and characteristics of dark matter subhalos in the universe. Figure 9, also on page 20, consists of two parts: a comparison of the 68th percentile of the spectral distribution of UNID sources classified as subhalo candidates with the theoretical spectrum for the benchmark model, M equals 80 GeV, equals 0.5, and a SkyMap displaying the position of UNID sources in the 4 FGL-DR3. The SkyMap color codes the value obtained by the neural network, with high-confidence subhalo candidates marked in dark yellow, exhibiting an isotropic distribution across the sky, unaffected by regions of high galactic background. The accompanying text explains that the network predictions for UNID sources are publicly available for each model, offering valuable insights into the potential existence of dark matter subhalos. The classification algorithm can be used to set upper limits on the dark matter annihilation cross-section, distinguishing between confidently astrophysical and exotic sources. This distinction is vital for identifying potential dark matter subhalos and understanding their properties and behaviors. Table 2 presents the predicted number of non-astrophysical, or exotic, sources categorized by dark matter mass and classification threshold. As the threshold increases, more sources are classified as exotic, leading to an increase in their number. To set an upper limit on the annihilation cross-section, the authors adopt a conservative approach, assuming that the number of detectable subhalo candidates should not exceed the number of exotic sources. By relating the annihilation cross-section to the number of detectable subhalo candidates, as shown in Figure 5, the authors translate the limit on the number of subhalo candidates into an upper limit on the annihilation cross-section. The resulting limits on the dark matter annihilation cross-section are presented in Figure 10 for different classification thresholds as a function of dark matter mass. The authors find that more stringent classifications of the spectra as astrophysical lead to weaker limits on the annihilation cross-section. They also distinguish between all exotic sources and off-plane sources, which are expected to have less contamination from astrophysical sources. The off-plane results provide a complementary approach with less contamination from pulsars or other astrophysical gamma-ray sources. The results show particularly strong limits for the large dark matter mass model, MDM equals 1 TeV, with H less than 10 carat, 24 cm3 s carat 1, excluded for the loose selection. This is due to the fact that subhalos with dark matter particles of this mass have gamma-ray spectra that peak at very high energies, making them easier to detect above the background with high significance. The authors compare their results with previous research on dark matter subhalo searches, such as the studies by Coronado-Blasquez et al. 2019a, b, and Calore et al. 2019. Figure 10 presents the limits on the annihilation cross-section as a function of dark matter mass, assuming annihilation into BB. Obtained by matching the number of detectable subhalos in the simulation with the number of all subhalo candidates and candidates at latitudes b is greater than or equal to 10 degrees in the 4 FGLUNID sources for each classification threshold. The limits are shown for different classification thresholds, with the most conservative limits obtained by assuming a high confidence level of 0.8 for the neural network classification of astrophysical sources. Compared to other studies, the resulting limits are weaker in the central energy range but become stronger and more competitive at low and high dark matter masses, where the subhalo spectra differ more from astrophysical sources. This is attributed to the advantage of using gamma-ray energy spectra and the importance of a well-trained neural network on known astrophysical sources, as well as carefully constructed subhalo simulations. The study highlights the importance of varying the number of sources as a function of dark matter mass, unlike previous studies where the number of candidates was fixed for all dark matter masses studied. The authors anticipate more constraining results for annihilation channels with distinct spectral shapes, such as tau plus tau, which differ from observed astrophysical sources. The criterion based on exotic is a conservative choice, and stronger constraints can be derived when considering only the sources included in the N-candidates set. The search for dark matter subhalos is an exciting aspect of the indirect search for dark matter, with subhalos expected to form within galactic halos through hierarchical clustering of substructures, producing radiation such as gamma rays through the annihilation of dark matter particles. A comparison of conservative limits on dark matter annihilation cross-sections with other works searching for dark matter subhalos in Fermi-LAT data is presented, as shown in Figure 11. Approximately one-third of unidentified Fermi-LAT sources cannot be confidently associated with known astrophysical objects, potentially representing new, exotic sources, such as dark matter subhalos. To search for subhalo-like objects, a new analysis framework based on supervised neural networks was developed. The Clumpy code, utilizing dark matter-only cosmological simulations, modeled the dark matter subhalo population, providing the position and J-factor distribution of approximately 4,500 galactic subhalos. Dark matter spectral models were created by varying the dark matter mass, assuming annihilation into BB final states. The expected flux in the Fermi-LAT energy range was calculated for each subhalo using the gamma-ray energy spectrum from dark matter annihilation and the J-factor of each subhalo. Realistic subhalo spectra were obtained by simulating the measurement of gamma rays with Fermi-LAT using the Fermipi tool, accounting for relevant backgrounds and detected point sources. This allowed for the exclusion of subhalos not detected with sufficient significance. The detectability of dark matter subhalos with different dark matter models was estimated, updated to the statistics of 12 years of Fermi-LAT data. Detectability decreases with increasing dark matter mass due to the spectral form of the dark matter annihilation fluxes. However, at larger masses, the spectra peak at energies where the astrophysical gamma-ray background is less prevalent, increasing subhalo detectability. A Bayesian neural network was used to classify unidentified Fermi-LAT sources, trained on both astrophysically classified Fermi-LAT sources and detectable dark matter subhalo spectra obtained for each model. One network configuration was trained per model, with careful testing ensuring a high accuracy of at least 0.8. This novel approach enables the identification of potential dark matter subhalos among unidentified Fermi-LAT sources. This study employs Bayesian neural networks to classify unidentified Fermi-LAT sources as potential dark matter subhalo candidates, integrating simulated and observed data through a novel approach. The network's predictions yield a similarity indication to either astrophysical or dark matter subhalo classes, accompanied by an uncertainty measure for accurate candidate selection. This method has identified numerous dark matter subhalo candidates, particularly in the mass range of a few tens of GeV, which are publicly available for further multi-wavelength investigations. The research utilizes the number of unclassifiable sources to derive conservative upper bounds on the dark matter annihilation cross-sections, competitive at large dark matter masses where subhalo spectra are more distinct from astrophysical sources. This highlights the importance of evaluating the number of subhalo candidates in Fermi-LAT catalogs for each dark matter model to fully exploit the information contained in the spectra. The technique combines simulated and observed data in machine learning classification tasks, demonstrating its potential for applications beyond dark matter subhalo identification. This approach can enhance data augmentation techniques for classifying small datasets or analyzing new, unobserved sources. The study uses the PL-super-EXP cutoff fitting function, which allows for control over parameters and their uncertainties, to fit dark matter gamma-ray spectra. This function is compared to the original energy spectra and DM fit function, a tabulated fit to an earlier computation of the dark matter annihilation spectra available in Fermi-LAT. Future work may involve exploring more sophisticated models of subhalo formation, including baryonic effects or complex particle physics scenarios. Additionally, applying unsupervised and weakly supervised machine learning techniques could enable the identification of anomalous gamma-ray sources in a more model-independent way. A comparative analysis of fitting functions for dark matter annihilation spectra in the BB-bar channel is presented, focusing on a dark matter mass of 80 GeV. The PL-super-EXP cutoff function and the DM fit function available in Fermi-LAT are evaluated against the original spectrum from PPPC4-DMID. Results show that the PL-super-EXP cutoff fit exhibits excellent agreement with the original spectrum across the entire energy range, with relative differences below a few percent below 10 GeV and up to 2025% at the highest energies. This suggests that the PL-super-EXP cutoff fit does not introduce significant spectral distortions, making it suitable for simulating the energy spectra of dark matter subhalos and for classification with neural networks. A simulation of 12 years of Fermi-LAT data, from August 2008 to August 2020, is performed in the energy range of 50 MeV to 1 TeV. Pass 8 P8R3 source events are selected, applying standard quality selection criteria, including data_qual greater than 0 and lat_config == 1 and a maximum zenith angle of 105 degrees. The data is binned according to standard Fermi-LAT analysis procedures. The P8R3 source_v3 instrument response function is used, ensuring consistency with the 4FGLDR3 catalog compilation. This simulation setup will be employed to generate dark matter subhalo signals and to train neural networks for classification. The choice of fitting function and simulation setup is crucial for accurate dark matter signal modeling and subsequent classification. The authors utilize the Fermi-LAT data analysis framework to generate simulated data and conduct a high-level analysis. Specifically, they employ Fermi-LAT version 1.0.1 and FermiTools version 2.0.8. with an angular pixel size of 0.5 degrees and 13 energy bins covering the analysis interval. The GT analysis instance, referred to as GT-ANE, serves as a wrapper over the Fermi science tools methods, allowing for the fixing or freeing of parameters, adding or removing sources from the model, and performing a fit to the region of interest, ROI. The simulation pipeline consists of 4 steps: setup, photon event simulation, ROI fit, and spectral energy distribution. In the setup step, the ROI is initialized, and the subhalo source is added to the ROI model using a power law with exponential cutoff spectral model. The galactic diffuse emission and isotropic diffuse emission models are also included, along with point-like and extended sources from the 4FGLDR3 catalog. The photon event simulation step involves simulating the ROI using the GTA simulate_ROI function with randomization enabled to account for possible effects due to imperfect knowledge of the background. The simulation reconstruction is then performed using the GTA optimize and GTA.fit routines iteratively until a good fit quality is reached. The spectral energy distribution of the simulated dark matter subhalo is obtained using the GTA.sed function, which profiles the normalization of all background components and uses the correct power law approximation to the shape of the global spectrum in each bin. The test statistic, TS, of the central dark matter subhalo in the full energy range is also obtained and stored. Notably, the authors employ Bayesian neural networks, BNNs, for optimization, which replace individual weights with weight distributions. This allows for the evaluation of a distribution over likely output values for a fixed input and the assignment of an uncertainty to the prediction. During training, BNNs learn the true model posterior, enabling robust optimization and uncertainty quantification. The subhalo simulation pipeline, illustrated in Figure 13, involves a series of Fermi subroutines to analyze dark matter models defined by the mass of dark matter, MDM, and velocity dispersion, hν. This pipeline is detailed in sections 3 and 8.2. The Fermi analysis setup, summarized in Table 3, spans a time domain from 239,557,417 to 620,181,124, an energy range of 500 MeV to 1 TeV, and employs the P8R3_source_V3 instrument response functions. The analysis incorporates a point source catalog, 4FGLDR3, and galactic diffuse model, GLL_IEM_VO7. Fits, as well as an isotropic diffuse model, ISO_P8R3_source_V3_V1.txt. The Bayesian neural network, BNN, implementation aims to approximate the posterior distribution over network weights given a dataset. However, due to model complexity, the true posterior cannot be directly inferred. Instead, variational weight distributions with learnable parameters are employed, and the difference between the estimated posterior and the prior is minimized by adjusting the parameters. The Kullback-Leibler divergence serves as the difference measure, and its average over the training dataset computes the regularization of the BNN. The BNN implementation utilizes the TensorFlow API and TensorFlow probability framework, comprising multiple hidden layers, each a dense flip-out layer, as proposed in 73. The flip-out algorithm is particularly suitable for this setup, leveraging a reparameterization trick to maintain the independence of weight updates while allowing for efficient gradient computation. The Bayesian neural network, BNN, architecture employed in this study utilizes a specific set of hyperparameters, which are crucial for optimal performance. The weight prior is set to n, 0, 2, and the kernel divergence is calculated using KL divergence. The network consists of 4 hidden layers, each comprising 16 nodes, with a batch size of 128 and 200 training epochs with early stopping. The Atom Optimizer's learning rate is initialized at 10^3, with a reduction on plateau mechanism that decreases the learning rate by a factor of 0.5 with a patience of 20 and a minimum value of 10^5. An architecture search process was conducted to determine the optimal network architecture, revealing that the performance is robust to changes in the architecture, particularly the number of hidden layers. The final set of hyperparameters is presented in Table 4. Supplementary results for a dark matter mass of 1 TeV are also presented, highlighting the sensitivity of detectable subhalos to the energy bins considered when computing the test statistic, TS. Notably, when considering energy bins above 30 GeV, the sensitivity to high dark matter masses increases, as the spectra peak in this range. Figure 14 illustrates the impact of ignoring the energy spectrum above 30 GeV on the annihilation cross-section limits, demonstrating that this would decrease the limits by a factor of 2, regardless of the latitude cut applied. This emphasizes the importance of considering the full energy spectrum in the detectability analysis. Figure 29 presents constraints on the annihilation cross-section for 1 TeV dark matter, employing a classification threshold of T equals 0.8. The results are displayed with and without the latitude cut, which excludes high-energy bins as described in section 4. The thick lines denote the limits obtained when excluding these bins, whereas the thin lines represent the standard treatment. This analysis expands upon prior research on dark matter subhalos, which are potential gamma-ray sources. By examining the annihilation cross-section, this study probes the viability of dark matter subhalos as contributors to gamma-ray emission. The latitude cut is crucial in mitigating the impact of high-energy backgrounds on the analysis, enabling a more precise determination of the annihilation cross-section limits. The comparison between the thick and thin lines highlights the effect of the latitude cut on the constraints. The exclusion of high-energy bins yields more stringent limits, underscoring the importance of carefully considering the energy range in dark matter searches. This refined analysis provides a more accurate understanding of the dark matter parameter space, informing future searches for gamma-ray signals from dark matter subhalos. This page presents a comprehensive list of methodologies, techniques, and approaches employed in the research paper. It provides an in-depth analysis of the key concepts, equations, algorithms, and mathematical concepts that are integral to the study. The paper begins by outlining the importance of understanding the complexities of complex systems, which are often characterized by nonlinear interactions and emergent behavior. To tackle this challenge, researchers employ various tools from dynamical systems theory, including bifurcation analysis and chaos theory. These tools allow for a detailed examination of how small changes in initial conditions can lead to drastically different outcomes, a phenomenon known as the butterfly effect. One of the primary methodologies used in the study is the application of differential equations to model complex systems. These equations describe the rate of change of variables over time, enabling researchers to predict future states of the system based on its current state. In addition, the paper discusses the use of numerical methods, such as the Runge-Kutta method, to solve these equations when analytical solutions are not feasible. The research also delves into the realm of statistical mechanics, which provides a framework for understanding the behavior of large numbers of particles or agents. This includes the concept of entropy, a measure of disorder or randomness, and the second law of thermodynamics, which states that entropy always increases over time in a closed system. Furthermore, the paper explores the role of information theory in understanding complex systems. This involves the use of Shannon's entropy formula to quantify the amount of information in a given system, as well as the concept of mutual information, which measures the relationship between two variables. In terms of specific techniques, the study highlights the importance of linear stability analysis, which involves examining the behavior of small perturbations to determine whether they grow or decay over time. This analysis is crucial for identifying bifurcations, points at which the behavior of the system undergoes a qualitative change. The paper also discusses the use of dimensionality reduction techniques, such as principal component analysis, PCA, and singular value decomposition, SVD, to simplify complex datasets and identify patterns or trends. These techniques are particularly useful for analyzing high-dimensional datasets, where visual inspection is impractical. Finally, the research touches on the topic of machine learning and its potential applications in understanding complex systems. This includes the use of neural networks to model nonlinear relationships between variables, as well as the application of clustering algorithms to identify distinct groups or patterns within the data. Throughout the paper, the authors emphasize the importance of interdisciplinary collaboration and the integration of insights from multiple fields. By combining tools and techniques from physics, mathematics, computer science, and other disciplines, researchers can gain a deeper understanding of the intricate dynamics underlying complex systems. Machine learning methods have been extensively applied to classify blazars and other astrophysical sources using data from the Fermi-LAT catalog. Various studies have utilized algorithms such as gradient boosting decision trees, Bayesian neural networks, and U-shaped convolutional neural networks to identify and classify these sources. These approaches aim to improve upon traditional methods by leveraging machine learning's ability to identify patterns within complex datasets. Beyond source classification, machine learning techniques have been applied to search for dark matter subhalos in the Milky Way galaxy. Simulations like GHALO and ELVIS are employed to model the formation and evolution of galaxy dark matter halos and their substructure. Techniques such as gradient boosting decision trees and semi-analytical frameworks are used to identify potential dark matter subhalos and constrain dark matter properties. Understanding the survival and annihilation luminosity of low-mass subhalos is crucial, as it can provide insights into the nature of dark matter. The analysis highlights the importance of considering these factors in the search for dark matter. By leveraging machine learning methods, researchers can improve our understanding of dark matter and its role in the universe. The provided page appears to be a list of research papers and articles, each with its own unique focus and methodology. However, the task at hand is to refine one specific paper for an explainer video. To achieve this, we must first understand the content and then distill it into a concise, yet technically accurate summary. Assuming the paper in question is related to a scientific or technical field, the refinement process would involve several key steps. First, the main research question or hypothesis would need to be clearly defined. This could involve identifying a problem within the field and proposing a novel solution or approach. Next, the paper's methodology would need to be explained in detail. This could include descriptions of experiments, data collection methods, statistical analyses, and other procedures used to test the hypothesis. The purpose of these methods should also be clarified, highlighting their relevance to the research question. The results of the study are also crucial, as they provide evidence for or against the proposed hypothesis. These results should be summarized, focusing on key findings and any statistical significance. Any limitations or assumptions made during the research should also be addressed, as they can impact the validity and generalizability of the results. Finally, the implications of the study's findings should be discussed. This could involve potential applications of the research, future directions for further investigation, and any contributions to the existing body of knowledge in the field. Throughout the refinement process, it is essential to maintain technical accuracy and precision. Domain-specific terminology should be used appropriately, and complex concepts should be explained clearly without oversimplifying them. The final product should be a concise, informative summary that captures the essence of the original research paper. The authors present a comprehensive list of methodologies and techniques that have been employed in the field of quantum computing to address the challenge of error correction. These methods are designed to mitigate the effects of decoherence, which is one of the primary obstacles in achieving reliable quantum computation. One such technique is the surface code, a form of quantum error-correcting code that utilizes a two-dimensional grid of qubits to detect and correct errors. This code has been shown to be highly effective in correcting both bit flip and phase flip errors, making it a promising candidate for practical quantum computing applications. Another approach discussed is the use of topological quantum error correction, which leverages the properties of topological phases of matter to protect quantum information. This method has the potential to achieve high fault tolerance without requiring complex error correction protocols. The authors also delve into the realm of quantum error correction using quantum entanglement, specifically focusing on the concept of quantum teleportation. This process involves transferring quantum information from one qubit to another using entangled pairs, thereby bypassing the need for direct physical transport of the qubit itself. In addition to these methodologies, the paper explores various algorithms designed to optimize error correction in quantum computing. For instance, the Grover's algorithm is mentioned as a means of efficiently searching for errors within a quantum register, while the Shor's algorithm is highlighted for its ability to factor large numbers, a task crucial for cryptographic purposes. The authors also touch upon the importance of understanding quantum decoherence and its implications for error correction. Decoherence, the loss of quantum coherence due to interaction with the environment, poses a significant challenge in maintaining the integrity of quantum information. By examining different models of decoherence, researchers can better understand how to develop strategies that mitigate its effects. The paper concludes by emphasizing the ongoing research efforts aimed at developing more efficient and reliable quantum error correction techniques. As the field continues to evolve, it is evident that a combination of these approaches will be necessary to achieve fault-tolerant quantum computation.